Start the recording, and we can get started. Alright, so yeah, here's a thing put together. We're some fourth generation reactors. I'm Sean. I go to Missouri S&T. I am studying nuclear engineering. Just always really liked it. One of my favorite things is fifth generation. I think that the benefits that we'll talk about. So I'm pretty excited to share some of this with you guys. I appreciate everyone showing up. Hopefully get some interesting things out of this. A little rundown on what we're going to talk about. So, I know not everyone knows that much about nuclear, so we're going to start just with some basics about nuclear power, how it works, why we're interested in it. Then we're going to move on to like what's the difference between the Gen 3 and Gen 4 reactor, and the other gens, really. Then we'll get a little more into Gen 4s, some fuel types, different kinds, and talk about why we like or why we haven't deployed them yet. Alright, so the basics of fission, a lot of it has to do with something called binding energy in atoms. Whenever atoms are bound together, they weigh less than the individual parts. So if you have a certain amount of neutrons or protons, and you weigh them all individually, it would be more than if you just have an atom of them. And what nuclear power is doing is basically taking advantage of this binding energy, because we want to change that. You're going to either break it apart or put it together. And right here, got a little graph. Anything past iron is going to fission because it has a more, or it's a less negative amount of binding energy per nucleon. And then anything below iron is going to fuse. And another thing to point out is why fusion is interesting. You can see the difference if we have deuterium and tritium. We're using those and getting up to like lithium and stuff. It's a big jump. You're going to get a lot more energy out of this jump than like uranium down to its components. So that's just the basic of where we're getting the power from. You can also, I use this equation all the time, E equals mc squared, because by finding the amount of mass differences on these nucleons, that's exactly how we figure out how much power we're getting. Turns out per fission, we're getting about 200 MeV of power. A pretty good amount per fission. Another little thing talking about why things fission. It has to do with stability. So as you're adding on more neutrons, we're basically just adding in more glue to keep everything together. That's how I always think of neutron. Glue in our atom. So we're trying to keep it as stable as possible. But eventually, the glue isn't going to hold as well. The more protons you have in there, the more it's trying to push the other protons away, it gets weaker. That's how we see this upward trend instead of just a linear fitting, as it gets weaker and weaker. You can see fission doesn't occur until all the way up here. The atom's trying to get to a stable point, and it just doesn't make sense to fission until that point. There's easier ways to do it. There's beta decays, which is you can either be expelling an electron, or you could be adding an electron for conversion into a neutron, so a proton. It can be alpha emitting, which is a helium-2 or helium-4 atom. And that's what most things do whenever they've got too much mass, is they'll try it to alpha, and that's what this is, this whole region. But then, like I said, fission doesn't come up to here, so we don't have fissile materials always on hand. And this is going to be really important for some of these reactor types that we'll get into. The thing to note is that the even isotopes are going to be a lot more stable. They're not going to fission as much. That's why U-238 isn't going to fission compared to U-235, because it's more stable. So basically anything odd, you're going to be able to fission a lot easier. And we also have these magic numbers of stability. Stuff like iron 56, it's got 2 magic numbers. That's why it's the most stable. So U-235, only natural fissile isotope. That's why we've used it. Why nothing else really compares to it right now. It's got a half-life of around 700 million years, which, in the grand scheme of things, is pretty short. It's still around, so it's long enough for that. But it's only constituting 0.7% of the uranium that we're getting. U-238 has a much longer half-life on the billions scale. And then the way that we get it, we basically mine uranium, we mill it, burn it by putting it in some acid solutions, get UF6, and then we'll eventually end up with CO2, which is what we're using for all of our current reactor types. And this is a problem because you have to enrich. Oh, yeah, you can, it would be in your settings, but I can, I'll slow down a bit. Is there any of those concepts that you'd like me to go over real quick? I didn't want to spend too much time on that. I didn't know how, caught up everyone was with, um,
Wait, Jill, try now. I muted everyone else so they wouldn't accidentally unmute. Oh, okay. I don't know what's wrong then.
yeah, on your Discord, in the settings, there's usually a section on the mic where you assign a push a talk button. I don't remember the default off the top of my head. But I can slow down a bit. So, yeah, U-235. Every time it fissions, we're basically going to have a spectrum of probability on what kind of fragments we're going to be getting. And that's shown by this curve right here. The higher the peaks are, more likely that product is. And it's given in percents. So the whole area under this is going to be pretty much every part we're going to get from it. And this is important because we don't always know what we're going to end up with. Whenever we get different isotopes, they're going to be longer half-lives, they might be more active, they might be more stable. We just don't know. So we kind of categorize these all into something called fission products. And that's really what plays a big role on things like nuclear waste, why we have the decay heat, that stuff's radioactive and we gotta let it cool down for so long. So it's just a big problem with fissioning. Yeah, I could see your icon lighting up, so I'm not sure why I wouldn't be able to talk. um yeah, another problem is since we only have 0.7% and it's the only fissile part, it's gonna take more than that to be able to keep this fission chain reaction going. The fission chain reaction is having to do with every time are we yeah, he's not muted. Everyone else is muted. He just couldn't find his the button for push a talk. Yeah, I don't know. But in our current reactors, we use light water reactors. Get more into those a little bit, but we're gonna need enrichment right now. And then the heavy water reactors, things like CANDU, using Canada, they're going to use deuterium as moderators instead of water, and that's going to allow for natural uranium, but they got to be a lot larger. It's more expensive. So it's really a kind of balancing act of, are we trying to enrich our uranium to be able to use it, or are we trying to use deuterium and avoid the enrichment process? But then we have to put more resources into reactors, and deuterium is just really expensive. And the reason that we usually use thermal reactors right now is this graph. It's a very important graph for nuclear. It has to do with the cross section per energy of U-235. And a cross section is a probability of interaction. It's really kind of hard to conceptualize because it has units of per centimeter squared. So it's technically an area unit, but it's a probability. And we usually give that in something called Barnes, which is 10 to the negative 24th centimeters squared, if I remember correctly. So just think of this as how likely we are to fission, because this is a fission cross-section. Cross-section is the likelihood of that happening. And we can see whenever we're in the higher spectrums of energy, it's going to be pretty low. It's a log scale. So we can see 10 to the 6, which is where a lot of neutrons are born, is almost 0. I think it evens out to around 7 Barnes. Not very likely. But whenever we slow down these neutrons, those moderators, water, then it's going to drop down to about here on the energy scale. Thermal is considered 0.025 EV, and it ends up being around 700 Barnes. So almost 100 times more likely to fission, just based off of that. But that's just for the current reactors. But that's why we want to thermalize neutrons. And then the problem with enrichment, like I said, most facilities use it. Almost everything in the US is light water reactors. We have to enrich to about 4%. It's just expensive. You have to diffuse it through these high pressure streams, and just to get to 99%, it's 1148. So we have to run it through these materials that many times, and it's just very expensive. Not a great way to do that. They're expensive to fabricate because the holes are on the nanometer scale, and we're just going to be running these through over and over again to get what we need. Obviously, not everything goes up to 99. Weapons grade is 93%. Highly enriched, considered about 20%. But it's not more difficult to raise once it gets higher. It's like to get to 0.7% to 7% is about the same as like 7 to like 99. It doesn't get more difficult, it just requires more. So we really want to try to avoid enrichment when we can, or trying to get more use of our fuel. And this is just a very simple equation for determining how many enrichments you would need, and this goes for anything. This is just specifically the number for U-238 and U-235. If you have purity assigned and you have an initial purity, so in this case, this will be 0.99, 0.07, and we have a diffusion coefficient, and the x here is going to be how many diffusions we need. So you can solve that for basically anything whenever you're trying to diffuse it. This is just for uranium. Talk about other enrichment processes in a little bit. because they play an important part in why we're not doing a lot of these Gen 4 reactors right now. So yeah, that was just a quick little what is fission. If you guys have any questions about that, let me know. I just didn't want to spend too much time on that because not the focus on today. But go ahead and get right into the generations of reactors. I know it's a little bit blurry. I couldn't find a better image, but really we have 4 generations, but it's kind of 5 because there's a Gen 3 plus. So Gen 1 is just the early prototypes. It was just testing, saying, hey, what works, what doesn't work. We're going to try all this stuff. Okay, that didn't work. Don't use that. Gen 2 was trying to actually put out these power stations. Really trying to get the power production going. This was things like RBMK, which was what was in Chernobyl. Obviously, we don't use those anymore. A lot of reactors today are still Gen 2 because most reactors are still old, 60 years. The one we're using on campus is just hit its 60-year mark, and that's really the point of a lot of reactors to Generation 2. Generation 3 and 3 plus are just trying to make Generation 2 better, basically. They're still building on the same concepts. They're not doing anything crazy. They're trying to get better yields, more safety, inclusive of passive systems. Because really, an end goal of safety is how much human can we take out of this to make it safe. You shouldn't always need to control something for it to not have something awful happening. So that was a lot of the goal of Gen 3, just improving the LWRs, trying to get better results. Now Generation 4, instead of just trying to stick with the norm, you're really trying to go off on these new ideas and concepts. And you can see the 6 different types we have right here. We have the gas-cooled fast reactor, lead-cooled fast reactor, molten salt reactor, sodium-cooled fast reactor, supercritical water-cooled reactor, and a very high-temperature reactor. That's a very original name, by the way. So 3 of these are fast reactors. We're really trying to hammer that in because they have a lot of benefits that we're not utilizing right now with sulfur thermal. So like I said, they're not really like what we're using right now. They're really trying to branch off because obviously nuclear needs something else to kind of come into its own. Like we need better ideas to justify its use. So yeah, Generation 3, focusing on improving Gen 2, trying to make it more economical, more feasible. A lot of nuclear cost is upfront cost. So trying to modularize these was a big component. Trying to just have them cheaper to build. Trying to put a more passive safety, not have void coefficients like in Chernobyl. Trying to make them easier to control. Higher burn up and operating life. Burn up is basically how much energy we're getting per the amount of fuel that we're getting as units of like megawatt day per ton. So just straight up energy per mass. We're really trying to get that so we're not having to fabricate as much fuel. Another thing is these typically operate at 75 to 150 atmospheres, which is very high pressure. And this is to avoid the water boiling. We need it in that liquid state for cooling purposes. So that's a very key feature on safety because hydrogen explosions are a big issue. That's what happened at Fukushima. It wasn't some kind of nuclear explosion that blew the tops off of those. It was the water, basically. So we're trying to get away from these pressure facilities. And then we're usually utilizing about 2-3 burn up, which isn't that great. Eventually we want to get to 100 because we want to use all of our fuel, not just a little bit. And since we're really limited to U-235 in these kind of reactors, we're using less than 1% of our uranium. We're not getting use out of all of our other potential resources. So, Generation 4, really trying to be more conceptual, think outside the box, has a lot of different fuel types. We're not going to go over all of them. A lot of them aren't even being deployed, but just the concepts for a lot of them are out there. And then we're also try to be more efficient, because thermal efficiency is a key factor in how much energy we're producing. A lot of Gen 3s are right around 33, 32, 33 range. So about a third of the energy we're producing can actually be transmitted to electricity. Meanwhile, Gen 4 is up to 50%. And really, this is based on how high of a temperature we're going to get. Because efficiency is based off your cold starting temperature and your hot temperature. We can't really have a different kind of sink than the outside world. So we're always limited on our basic outside temperature for efficiency. So our only real ability to increase this is by making our facilities hotter, which is, in a lot of these, is going to be a lot hotter than what we're used to right now. And then here we have just a few pictures. You'll see more of these a little bit more whenever we talk about them. But, and we can see just the wide variety of the vessels, and they'll just look a little different from each other, not all just copy paste LWRs. Here again we have the 6 different systems I would talk about, and then I mostly have this here for the temperature of the coolant. See, it gets, especially on the VHTRs, they had an original goal of around 1100, but material science has been kind of getting in the way, so we keep lowering it. And right now we're kind of shooting for 900, 850, hoping to eventually reach around 1000 Celsius. Very, very hot. Most materials can't do this, so that's a big issue. But the main thing is these efficiencies. So the other one, 33, they have a max of 50 on supercritical water, but all of these are at least 42. It's the lowest. So all of them are about 9% more efficient. That'd be awesome for our production needs. Also see the fuel types that we'll get more into a little bit. And for neutron spectrums, we have 3 that are just fast. VHCRs are only thermal. Supercritical is both. And MSRs, it says thermal and fast, but what's the variety? We can actually make concepts for epithermal in the middle. For exact numbers, a fast reactor is around 1 MeV of energy in a neutron's thermal. Technically, a thermal neutron is 0.025, like I said earlier, but whenever it's around 0.1 or 1 EV, we'll consider it thermal at that point. But you can even make it between that range for these MSRs, because they're just really diverse how they operate. So, thermals, yeah, less than 1 EV. Really gotta slow it down. It's gonna require moderation. Basically, moderation is putting something in to collide with the neutrons. You can't really slow it down with things that require charge. You know, it's not gonna have any Coulomb forces dragging it down. You gotta put in something that's gonna be interacting with. A lot of it's water, a lot of it's deuterium, graphite. Those are the main 3 ones that we've always been using. Water is wonderful because whenever you're, if you think of a game of billiards, you can shoot a ball at another one, and you can transfer about all your energy from it. But imagine you're shooting a golf ball at a bowling ball. It's not going to slow down as well. So you want something as close to that mass as possible. And that's exactly what water gives us, because it's mostly comprised of hydrogen, which in its essence is just a proton and electron. You have a neutron striking a proton, they're basically the same mass. So that's why water is so great for cooling or our moderating needs. It's really cheap, it's great at slowing down. The only problem with it is it'll absorb neutrons, so it's not technically the best moderator. That goes to deuterium or H2. Like I was talking about before, even though it doesn't absorb as many neutrons, it doesn't scatter them as well, so you have to have the reactors larger. CANDU reactors are going to be bigger than the ones that we have in the US and in other places, because even though they have a better neutron economy, they don't need as many neutrons produced. It still needs more time to slow down. It still needs more interactions. Ideally, Ethereum will be used more, but before it's just really expensive. Can't afford to put in everything, so it's a really balancing act. We need fissile fuel in these thermal reactors. Obviously, U-235 is what we always use. So these are usually used for a once-through fuel cycle, which is what we use in the US. I'm not too familiar with other fuel cycles. I assume in France, I think in France they're using more of a closed. But basically, once through, you put your fuel in the core, does this thing, then you just set it somewhere. Which is why a lot of people have these problems with nuclear. We're just setting it somewhere. We're not doing anything with it. It's a big issue. And on the other hand, we have these fast neutron reactors. So we're not trying to moderate them. We're not trying to slow them down. We're keeping them in that high energy range, that MeV range. So the high energy prompt neutrons are triggering fission here, because you have something called fast fission, which uranium-238 can utilize. So even though uranium-238 isn't considered fissile, it can still fission. It just needs an extra push. People don't call it fissile because it's not good at fissioning in the thermal range. The fast range, on the other hand, it can. And another aspect is capturing these neutrons, converting them into something that is fissile. So whenever we have uranium-238, we can capture a neutron and then eventually turn into plutonium through a few decays. And plutonium-239 is the best fissile material in the fast range. Can produce the most neutrons per fission, just the best. On the other side, we also have thorium, which can capture a neutron, turn into protactinium, which has a half-life of about 27 days. That'll eventually turn to uranium-233, which is the best for thermal ranges. So even though we use 235, it's not the best in any regards for its efficiency in creating neutrons. But it's just what we have to use, because we don't have these stocks of uranium-233 and plutonium. And plutonium, it's a lot easier to make things like bombs and everything, because you need a lot less. It's just better at producing those neutrons. We really don't have a lot of practice with these kind of reactors. We have around 400 reactor years, which is kind of what it sounds like. It's the amount of experience for a year in a reactor. So it's not that we have like one running for 400 years. It's that we have about 20 facilities and they've averaged about 20 years of practice. But obviously that's nothing compared to the other types that we're using. And these are intended for a closed fuel cycle. So instead of just taking a waste and throwing it out somewhere, we can basically just put it back in. Since we have this stuff that can keep activating and producing fissile components, you just keep using it. Obviously, there's some limitations on it, but wonderful for getting down these fission products that we talked about earlier. The actinides, because the minor actinides play a big role in the thermal heat and half-life of the waste that we have. So it usually requires more enrichment to get it going because the neutron economy isn't as great. You need to have a little more push to have the other isotopes doing their things. And it requires higher flux, which is the amount of neutrons like in an area. So they're a little harder to get going, but overall the advantages of a closed fuel cycle are really hard to counteract. But yeah, we have the higher burnup of actinides. Actinides are a section of periodic table. You have actinides, lanthanides. It's one of the two that are like down at the very bottom, like separated from the rest, because they don't really fit into the tables that great. Your major actinides are uranium and plutonium, and your minor actinides are things like neptunium and americium, the things over here. And we're interested in this because we can use our resources. Like I was saying, you can't just directly put it right back in, obviously, but you can use more than just the 0.7% of uranium you're using before, which gives a much bigger lifespan to our resources. So by deploying these instead of just using our U-235, we can get about 45 billion years of energy. That's just from the fission. Right now we're only estimated at 230, so we don't have we have a lot of uranium, but not that much. But if we're using U-238 and eventually thorium, I mean, we're not going to run out of this stuff anytime soon. And uranium-238 is technically a renewable resource because it can be extracted directly from salt water, things like that. So you're really not going to run out of that. There's so much in the ocean that we're not even touching because of the cost to get it. It would just be much more beneficial, and we're not going to run out. So breeding is another very important thing. It's getting the fissile material from the amount that you're putting in. Like I said, you have your uranium over to plutonium. Since if we end up with more plutonium than we started with uranium-235, that's good. We have more fissile material. Exactly what our goal is in these fast reactors. Whenever we're converting more fissile than we're using, that's called a breeding ratio. Not ration, that's a typo. But that's great. Ideally, we would get that, around 2 would be awesome. We're still working on the specifics of it. Obviously, it depends on the reactor type. But anything above 1 on converting is called breeding. And 3 of these Gen 4s are fast breeder reactors, or FBRs. So, we'll get into those in a little bit. To get a drink real quick. Alright. So, these fuel types. It's a pretty big change from the iridium dioxide that we're used to. One thing that's really interesting, especially to me, is these triso fuels. We have them pictured over here on the right. They're very, very tiny particles that have our fuel in the middle. It's a fuel kernel. Then you have a carbon buffer that's used for things like expansion, keeping in fission gases, things like that, not letting it break out of its shell. It's kind of like a little, not really like a sponge, but just an area to let it move and expand, things like that. You have silicon carbide, some carbon, and graphite, which is our moderator in this case. So instead of having to have these separate moderation issues, we have them right here in these spheres. There's two different ways to basically utilize these triso. You can either go to prismatic route, where I mean you can see how small these things are. They're like 0.9 millimeters, uh, and basically centering them into these compacts of prismatic field elements. You can just have straight up field elements using those, or you can have a lot. I think it's around 11,000, and one of these it's about the size of a tennis ball. You can see, and it's these like called pebbles, like a ball of this triso with the graphite matrix around it for moderation. So very interesting. Very expensive to produce. Right now, our uranium dioxide is around $300 per kg, I think. These are about $5,000. So the manufacturing is to be desired, but they have a lot of potential. We can justify their use, I should say. Yeah, pebble bed, prismatic, different uses in the reactors. And we also have things like UCO, which is going to make less carbon dioxide gas, which is going to lead to more particle failure or the amoeba effect. So those are better for particles failing. You have nitrides. Nitrides are interesting because they're a lot more thermally conductive than uranium dioxide, and they have a higher melting point, and are overall just better for heat capacity. But the problem that comes with these nitrides is nitrogen 15. Nitrogen 15 is going to absorb neutrons, and it's just a pain in our butts. So what we really want is nitrogen 14, and the only way to really get that is enrichment. But you've never really heard of a nitrogen enrichment facility, have you? Don't really use them. That's really what's holding that back. Very cool concept, very efficient, but we have to enrich it before it is feasible. You got metallic alloys, you got zirconium alloys, you got all kinds of metals pairing with this uranium. You have carbides, salts we'll talk about, but I mean it's a load of different fuel types for these. The most important one really is these triso, because it's the most advantageous, I think, if we can get it to be a little cheaper to manufacture. So, onto our actual reactors. First, we're going to talk about the supercritical water reactor. Supercritical here is not referring to the neutron population. I'm sure you guys have heard of the concept of criticality. When something is critical, it means you're producing just as much neutrons as you're consuming. If it's supercritical, you're producing more than you're consuming. And supercritical is a runaway reaction, basically. You don't usually want that. Not the neutron population. This is the moderator. This is specifically supercritical water. Supercriticality is a point on these liquids where it's not a gas or a liquid. It's pushed above those extremes of temperature and pressure, where it's something in between. It's almost like a very saturated steam. And this has a lot of advantages because this is saturated steam. It's still very dense. It's still going to moderate your neutrons. It's still going to give you all the good stuff of the water moderator. But you also don't need to boil this water now and turn it into steam for your power production, because this supercritical water can just be used straight into the turbine. So obviously you're kind of taking out a lot of steps by just having this supercritical water. The design really simplifies down if you have this. The problem is beforehand getting the water supercritical. That's the only real issue with this. Another thing is the pressures required. Talking about, we don't like having high pressures before, and keep it in this state, it's got to be high pressure. So that's one major issue with this. Um, but you also don't have to worry about boiling because it's already past that stage. So you can operate at higher temperatures than the light water reactors. And there's also no void production. And I used that word earlier, void. So what is the void? It's really in water, you can have like it really just like a literal void in water. It's this area where you don't have the effects happening. You're not gonna have the moderation, you're not gonna have the cooling. It's these little areas that are a big problem. Uh, as a word you might come across is a void coefficient, which is a big problem in Chernobyl. Whenever we had the void coefficients, they didn't understand what it was at the time, and by not having those areas of cooling, it basically just had the energy range where it could keep producing these reactions. The voids are a big no-no in nuclear. We don't like them. We want to get rid of them, and this helps with that a lot because it's just steam. It's not going to have those voids as regular water can have. So these are interesting. Like I said, pressure not great. VHCR. We currently have HCRs, high temperature reactors, but it's just very high temperature now. Um, and one good thing about having higher temperatures is you can make them smaller. By having the higher linear heat rates, you can make these more compressed, and that's an end goal for SMRs, other things like that. Is really trying to compress our power densities and safety features so that they make sense to make small. Because if you have like a really low power density, there's no point in having it. But you're really not going to have gas cooled for a lot of SMRs. But still, having them smaller is always going to be better for fabricating and material cost. So in this case, helium is used as our coolant. Um, you can also use supercritical carbon dioxide, depending on the applications. Helium has its problems. It could be well, it's inert, but you usually don't use helium that much for coolants. But we also don't use gas cooled a lot, and I'll talk about why. And but since you're already having the coolant and a gas, you don't have to worry about it boiling. Like we talked about earlier, it can be up to 1,000 degrees Celsius. That's our end goal right now. It's more around 850, 900. And since it's this high temperature, you have a very high thermal efficiency, which is awesome. And then moderation here is actually graphite. And I talked about deuterium earlier as being the best moderator. And there's really better options in graphite like beryllium and water. And the reason that we use graphite is for structural integrity. In this instance, we can't have a moderator that's not providing a structure. So that rules out deuterium. And beryllium, oh, beryllium, toxic, it's expensive. It has very good moderating properties. I like to eventually utilize it in some cases, but the toxicity just doesn't want to be dealt with right now. And you can see in this specific one, we're using the pebble bed. So these are the triso pebbles that we talked about earlier. And something that's really interesting about these is you can really just drop them into these reactors and have the spent ones go out instead of having to turn your entire reactor offline, having 2 week period where it's not operating. Just drop in more fuel. It's a very efficient system. I mean, theoretically, you never have to go offline, which is awesome. And the other thing is, whenever you have such high heat, is you can have other applications for heat, like hydrogen production, and I'm not too sure all the other chemical processes that people want to kind of exploit with these. The main one is the production of hydrogen, but there's a few others. So MSRs, these are I don't want to say like the most promising, but they're definitely the most interesting of them, I think, because you're really not limited in a lot of ways. You can use whatever neutron range you want. Um, the nuclear fuel is cooled with salts, which is going to heat water with a heat exchanger. But you can also just melt your salt in. So you have your fuel and coolant in one substance, which is really strange for compared to other reactors. We've never really done that before. Since these salts are so hard to melt, you also can operate at 1 atmosphere, which is really ideal for safety features because anytime we can get rid of pressure, we want to. Pressure is never good for materials, basically always going to be a hazard. So having the 1 ATM is a big safety feature on these. Just two different designs. Usually we just use single fluid designs, meaning we have everything just in one soup. Not really a soup, but you have everything together. The two fluid design is going to have your fissile and your fertile components separated. So you're going to have like your uranium 235 and stuff in one solution and have your things that you want bred in another solution that are separated. A little more a pain to create, so we usually stick with single right now. And since everything is kind of in this liquid form, you can actually have these passive drain systems where you just basically break open a pipe and the liquid will just go into these cooling areas where it can cool off and become inert. So it really takes away a lot of possible uh, design issues for safety. And these were actually investigated a long time ago by Oak Ridge. I want to say in the early 50s, and they were being researched for aircraft reactors, which would have been really cool to actually have by now. But unfortunately, Oak Ridge's funding on this didn't really go great. Got canceled. They had a few concepts written up, but it never really made anything. And they're kind of getting looked at again now off of some things. And here we have fluoride salt cooled high temperature reactors. So they may sound different, but these are really still MSRs. But instead of having the fuel melted in with these salts, we're going to have a solid fuel here. And it's really taking a lot of basis from other reactors. Like we're having the high temperatures of HCRs, having the salts obviously. But you're taking a lot of these components and getting kind of best out of all of them. You don't have these high pressures, takes away a lot of the risk of explosion, other things like that. And those are like in these LWRs and HCRs. But at the same time, we're getting in that such high temperatures that they're really efficient for thermal production. Even more so in like the sodium fast reactor that we'll talk about and a lot of other reactors. So 700C is very high for current standards. So it's kind of taking a lot of different components. And you're usually using fluoride salts. The two main candidates for salts on the MSRs are fluoride and chloride salts. Each kind of have their issues. I'll talk about those in the next slide. And then FLIBE is the main salt component that's being looked at. Fluoride, lithium, beryllium, mix of those. And these will also use like triso fuel instead of just dissolving uranium straight into the salts. Ideally, it would be triso fuel, like I said. Expensive, kind of a pain. I use a similar Braden cycle. Just Braden and Rankine cycles for power production. Why do you use Rankine? And then heat removal from salts is wonderful. That's why we're looking into these salts because they have such a high heat capacity. Another thing with these MSRs is you can do a lot of the operations online since it is a liquid fuel. You can almost like filter it out into these chemical processing plants to take out actinides directly, and that'll help a lot in the long term with the activity of your waste, other things. But that's a lot of chemical problems, so I don't touch too much on that stuff. But it is part of it is the chemical processing plants. Another thing with these FHRs is they're more power dense because they're not gas cooled. Gas cooled reactors are never going to be very power dense because gas just can't cool effectively. Since it doesn't have a very high density, it's not going to be ever able to cool as well as these other designs. So these are a lot more power dense, which gives it an edge. Because power density is kind of a double-edged sword. Uh, it means it's going to be more dangerous to operate, but at the same time, you need less materials. So take was that what you kind of prefer. And then for assault types, three main ones are being looked at: Lib, Flanock, and then NAF, CRF4. Lib has the most potential, so that's what we have over here. Be it both its solid and liquid form. You would just straight dissolve. Like in this case, it's uranium 233. Just have your fuel in there. That's really what you use in your reactor. Few problems though with the lithium based salts is tritium production. Tritium is not a great thing to produce. It's what's in hydrogen bombs. It's really active. It's just not great to have. A lot of proliferation issues. So we really want to try and avoid that. And with that is enrichment. Again, we just want to have enriched lithium, but we don't have those facilities right now. So that's a big issue, is we're going to be having these H3 atoms that we don't want. Chlorides, on the other hand, are going to also need enrichment for the higher breeding ratios because they're not as effective on the other components or just isotopes. The both need enrichment just for different reasons. Lithium is a little more promising, but nothing's perfect yet. GFRs, so we have gas-cooled fast reactors. So they're using the same high-pressure helium as the VHCRs. These ones are going to be in a fast neutron range instead of the VHCRs, if you remember, are in thermal. I talked about earlier. It's only one that only operates in thermal. These are very good at actinic recycling, which, like I said earlier, is things like neptunium and americium, things like that. Basically everything around uranium plutonium that's not uranium plutonium. It's going to require, like a lot of these designs, more advanced materials and fuel. That's really what's holding us back on most of these designs, is just the fuel. Salts are very corrosive. That's why we haven't been using MSRs, because we haven't really found a way around this corrosive aggregation of materials. We're trying to find stuff that can withstand it, and the high temperatures too. Most things don't want to be near 1,000 degrees Celsius. So it's a big issue of trying to have things that can withstand these circumstances. And even if it can withstand it, other potentials like creep, and those are just radiological effects that over time are going to make these things fail and brittle. So these are using a silicon carbide cladding around their fuel. Eventually, we're looking at carbide fuels. Carbides are really good for high temperature applications. They got really good creep. Creep is basically the defects in a material advancing over time. You think of it like if you have an atom out of place, and over time you'll have 3 more atoms out of place. Just as time goes on, you're gonna have more displacements, which leads to more chances of failure, and it changes the properties over time. It's a big part of construction, but specifically in nuclear applications, with all the radiation, it plays a bigger role. And you have to understand the creepier materials. Like, how long is this going to be able to withstand displacements? Or how many displacements is going to be getting from this kind of radiation? The creep is just basically a measurement of this material failing. So that's a big section of a lot of these materials is even if it can withstand it right now, is it going to be holding up in 5 years? If not, we can't really use it. Yeah, hopefully that. Yeah, basically of the materials, just the and it doesn't always go exponentially. It can be more of a linear. It really depends on material, but it's just a term for the eventual failure, basically. Some things are gonna have more vacancies than other things, but yeah, it's just very specific, and it's really material sciences are very complicated, and we're getting a lot of advancements lately, which is why we're looking back into these. But before, not a lot of these concepts were understood very well. We just knew, hey, stuff's breaking. We don't know why. That was responsible for a graphite fire in a reactor a while ago. It's called Wigner energy, where you're having radioactive displacements in your graphite that's storing heat. And eventually that heat got so extreme that it just caught all the graphite on fire. And they had no idea why. But now we're understanding these concepts better, so we can kind of make more advancements in these materials without stuff catching on fire. So yeah, materials are really the main part. That and the like enrichment of the products. These are really these GFRs are trying to get higher burn up. I said always good. Very much always want a high burn up. You want to be using less fuel for more energy. Your safety margins. All of these are trying to include more passive, but since these are gas cooled, less power dense. Like I said, good thing or bad thing, depending how you look at it. I look at it as a bad thing, but if you're really concerned on safety, or I look at it as a good thing. No, I look at it as more power dense as a good thing because you want less materials, but at the same time, more dangerous. So it's a trade off game. And these last few are going to be liquid metal coolant. These are a little different than what we're used to. They're great heat conductors. They have different safety systems though, because if you have liquid sodium and you try to use a sprinkler system for a fire, you're not going to have a very good time. Sodium is just going to explode. So you really got to get a little more creative with your safety system upon these designs. Things like sand and other suffocating types of safety systems are needed. They have really low melting temperatures. Whenever you combine metals together, they actually typically get a lower melting temperatures than independently. And you'd be surprised how low some of these melt. Things like lead, and I mean, lead only has a melting temp of around 600 C, I think. That's a really low moderation, which is exactly what we want for fast reactors. We don't want it to end up in this little epithermal range where it's not going to be getting enough energy for fast fission, but not getting down enough to induce thermal fission. So low moderation is good in this instance when we're designing these fast reactors. Higher power density than gas, and the two that we're looking at right now are sodium and lead, but they each have their own little issues. So sodium cooled, obviously liquid sodium metal is going to be the primary coolant. There's already a lot, I won't say a lot, but these have been made. The BN 600, which is 600 megawatt. There's BN 300. They're trying to work on a BN 800 right now. Actually, I think it got deployed in 2014. but these have been made. They were used for water distillation in areas that didn't have a lot of clean water. So they've been deployed out in places like that. Uh, these can also operate at 1 atm. The low pressure, better. The metal here is going to be less corrosive than the salts and MSRs, but like I was talking about, you have the reactiveness. If this comes in contact with water, it's going to be awful. You can't have that. You can't have. I was watching a lecture at MIT for some of these, and the instructor said that he was in a facility where they were using this type of reactor. He just asked where the bathroom was, and they said, "We don't have a bathroom here. We're not going to put a plumbing system in this building. You're going to have to go to the next building over if you want any water, because you can't have that reaction happen." So that's a big issue with the sodium usage, but it has the best breeding ratio and lowest moderation of the metals that we're looking at. So it's technically the best if you're careful with it. And these, like other fast reactors, are for burning actinides, breeding your fissile materials like plutonium, uranium, all that good stuff. And I didn't directly mention it before, but these fast reactors are the only way that we can really utilize thorium, because thorium 232 is really like uranium 238. It is fertile. It needs that push to either produce something or fission itself. So we really can't utilize those resources without these fast reactors, and thorium is 4 times more abundant than uranium. So being able to use it would be very advantageous, but it's kind of overrated in some regards. I know a lot of people really hype up thorium, but it has its issues. It's a lot harder to control. Uranium 233 is a lot harder to control in reactors because its prompt lifetime is a lot shorter. You have less delayed neutrons, which is what we control reactors. So it definitely has its issues. But having that extra tool to use would be beneficial no matter what. And the fuels are usually metal or MOX alloys. MOX stands for mixed sorry, mixed oxide fuel. And this is, the oxides are basically referring to uranium and plutonium. MOX is what comes at the end of a reactor life after you have your spent uranium and you mix it with plutonium, and then you basically shove it back in the reactor. It's what we're using right now. You can use it in the thermals. You can't use a whole lot of it. Up to like 30% is safe, but you can't just fuel a reactor on it. Plutonium is actually really heavily produced in reactors. Not a lot of people talk about that. At the end of life, plutonium is making up about a third of your power production. It's a very good chunk of the power that we get from these thermal reactions that we're using. So mixing it back in and putting it back in the reactors is very viable, and it helps use it up, because we don't want plutonium sitting around. Like I said, it's great for bombs, and you don't want it sitting around. So these are good for using those types of fuel. And lastly here, we have the lead-cooled fast reactor. So it's using a lead bismuth mixture with a very low melting point. Like, I was surprised at how low this was. 123.5 degrees Celsius to melt metal. Like, it just doesn't seem what you'd usually think of as being hot for metal, but it's very good for these applications, because you don't want your metal coolants to be getting past this point. You don't want it solidifying, because you're going to run into a lot more issues if your coolant is solidifying in your reactor. So having it lower is always going to be better in these applications. So that's a good thing about the lead. So cyanide is really similar to the liquid sodium, but you're basically just replacing the coolant. Not too much else going on here. So the lead is not chemically reactive with air or water, unlike sodium, but it is corrosive, very, very corrosive. A lot of similar issues as the MSRs, where the materials just aren't able to withstand it right now. So because of this corrosiveness, sodium is usually more um, considered like the better of the two. Sodium's kind of considered the best out of metal coolants. Um, but lead does have a higher melting point than sodium because sodium, I want to say it's around 90. I can't remember off the top of my head. But both of them are really low. And lead on its own isn't this low, but when you mix it with bismuth, like I was saying, when you mix metals together, they usually have a lower melting point. Another aspect is you can just take out the entire core, which usually doesn't sound like a very good idea, but in more rural areas, it can be beneficial because you can just basically deploy a new core out there instead of having to have all these systems set up. So it has its applications. I'll just put it that way. It does have a lower void coefficient than the sodium, which is good. Void coefficients are never very good. The less voids we can have in our coolants, the better. And these have also been made before in the Russian Alpha class attack submarines, which are pretty interesting. So, Russian attack sub, first commissioned in around 1971, but these things were fast. At the time, I mean, 50 miles per hour on a sub, that was crazy fast. It was so fast, it was outrunning torpedoes. Like, they could not catch these things. And it could maintain this speed. This wasn't just like a little burst. It could have that speed for a while. To just, it's almost like a panic button. You could have all your power going straight into your lead bismuth reactor. And yeah, there might be some radiation effects, but would you rather risk that or blow up from the torpedo? Usually you're gonna want to risk that and try to escape the torpedo. So eventually they actually had to make torpedoes for these things because you couldn't catch them. So I thought that was really interesting having these reactors in there. The Blackbird, yeah, yeah. I mean, obviously subs have uh advanced more and torpedoes, but I just thought it was interesting having these deployed so early. So yeah, some overall advantages that we're kind of talking about: the closed fuel cycle, being able to use all of your resources is such a key point on these. Having the higher burn up is always going to be better. Um, and whenever you're burning these actinides, your waste really doesn't become that much of an issue anymore. Having waste only lasting centuries rather than the thousands of years right now is really key for advocating nuclear power. Because a lot of people just say, "Oh, what are we gonna do with waste? What are we gonna do with waste? What are we gonna do with waste?" Well, there really isn't a lot of waste now. You're also getting less waste, as you can mix them back in, put it back in reactors, deploy it into MOX fuel. All these other opportunities on these fast reactors. These are just for the fast reactors for these few. Obviously, the actinides are still going to be making power since they'll be transforming and getting off their heat. And then a lot of key safety features, getting away from the pressures, trying to avoid hydrogen explosions, really trying to avoid water. Doesn't really sound like something you typically think of, but getting water out of our systems is really a good thing. It doesn't bring a lot of good right now, besides just moderation. We use it because it's cheap. We use it because it moderates good, but it has its issues. It's really well understood. You're never really going to be surprised on how water behaves because it's so studied. You know all the numbers very well. So that's why we use it a lot right now. Uh, we're over here. We kind of have the actinides I was talking about earlier. This whole row. Here you have uranium and plutonium, your two major actinides, and then yeah, your minor actinides. Anyways, these are what a lot of the half life comes from. And for the disadvantages, some of them are more complicated, some of them aren't. That supercritical water reactor simplifies things, but on other things like the sodium cooled, it really is more complicated trying to put it all together. The materials needed need to be able to withstand these kinds of extreme temperatures and corrosivity depending on a reactor. Uh, Enrichment would be needed if we were going to use like the nitrogen fuels or the lime chloride based salts. Some designs are theoretical. Most of them have been kind of tested, like I gave you examples of the two metal cooled fast reactors. They've had designs and prototypes of MSRs, but other ones haven't been completely proven, and they have different deployment kind of chances, I guess. Some of them are a lot more likely to actually come into fruition. Licensing is hard because anything away from our light water reactors right now, people don't like change, especially government. So especially these gas cooled, like they're a lot different than what we're used to. Being able to justify their use is very difficult. Like, because we need new rules, we need new regulations, we need systems and requirements for those systems. The licensing is very difficult. It's a big roadblock ahead. But if we can get around that, if we can justify the use of these, if we can get these good efficiencies, good productions, then overall it would be wonderful for being able to use more materials, being able to produce more electricity, having the higher power densities on some of these cases. I'm very optimistic about these. They definitely have a work ahead of them. So do you guys have any questions about anything we talked about? Even just from I know I went through the basics really quickly, but what's my favorite reactor design? I am personally a really big fan of MSRs. I think that the potential for them is just really high. You can do so many different things with them. You can have the solid fuels, liquid fuels, and salt in itself has a very good negative temperature coefficient, which is exactly what we need for safety systems. Because as the temperatures get higher, the salts expand more, which makes the fuel. Yeah, MSRs. Yeah, but as the salts get higher, they try to expand more, and in turn, that means less neutron economy because your fuel isn't as dense. So whenever it's not as dense, it's less likely to interact. So salts are innately very safe, and obviously the auto drain systems are awesome. I'm a big fan of MSRs. Do all Generation 3 light water reactors have passive autocatalytic recombiners? Not all of them. Um, we're trying to work for it more, and like I said, a lot of Gen 3s aren't even support. A lot of what we have right now is still Gen 2. I couldn't give an actual answer for all Gen 3s. I only know what we do in the US, and we're trying. All I can really say. We want to have those kind of recombiners, but it's rough out here. And why isn't the US doing anything with the waste? That is purely economical. It does not make sense with your money to put the waste back in. because uranium is so cheap to just grab out of the ground and throw in a reactor. It doesn't make any sense right now to reprocess it from their point of view. Obviously, in a long run, you need to reprocess. You need to have the closed fuel cycle, but the U.S. just doesn't want to deal with it right now. But we're also not burying the fuel, so we're not putting it off limits from our use, but we are just kind of having it out, and a lot of them are in the like spent fuel pools. If you guys have ever seen those, it's basically just these giant like literal pools of water where they put in the fuel to cool down for a little bit, and a lot of it just sits in there for a while. They'll go to dry engineering facility storage, but it's kind of just sitting around right now. Still saying changes with it. What materials will we need to develop to deal with corrosive effects of salts? That is what we're trying to answer. I'm not too familiar with the materials. I was going I was actually going to be designing an MSR right about now, but because of the materials, I had to switch because we don't have a lot of the data that we need for that. A lot more data needs to be collected for these, which is really a problem of even researching them. Is you just don't have the numbers. We don't have the test for it. So that's a big part of material science right now that we're trying to get around, is getting the data collected, trying to find what exactly, and it's different corrosivity issues depending on the salt types. So you really have to pick your salt, pick what kind of materials you're interested in, and go from there. Because FLiBe and chloride-based salts aren't going to react to everything the same. How is France's electricity cheaper with reprocessing? Well, it's overall it can be cheaper by having these facilities already. Like they'll have the separation facilities for plutonium where they can recombine this stuff. And then, when you think about it, it makes more sense economically to be using all your fuel. And another part of the US not doing it is licensing issues and such, because we don't have these requirements out for, hey, how much MOX is safe in a reactor. Obviously, we have numbers theoretically, but you can't just plug in that maximum amount and expect the uh, NRC to be happy about it. They are very, very strict here. They need a lot of proof before you can really do. They need a lot of proof of concept. So it's just a big mess. But yeah, France is doing it well. They're reprocessing. They're trying to switch over these fast reactors more. So we need to be more like. Yeah, France obviously has really cheap electricity. They're doing everything great. So hopefully we can kind of go over to a closed fuel cycle eventually with some. Yeah, in the future. But then needs more of these fast reactor design, which is why these are important. Because, like I said, right now with these LWRs, it just doesn't make any sense. So I just have a few questions for you. So why are we interested in fast reactors? I know I talked a lot about them. So what makes a continuous feed more desirable? Like I said, in the liquid salts, you have these chemical processing plants where you can just keep feeding the stuff in, and these pebble beds, you just drop the pebbles in. So why do we want that? Why do we not want these things offline? And what kind of reactors do you guys like? Is there any that kind of stuck out to you? Uh, Things that you really like that we need more of? Kind of reactors do you guys like? So let's kind of think about that stuff. Hopefully, got a few things out of this. If you guys have any other questions, let me know. that was a lot of what that's not like super technical and boring. But if you guys need any extra data or anything, but I didn't really provide a lot of like the cross sections for uranium and thorium and all. Yeah, either my work's cited. A lot of this was from Syed Alam, my field cycle professor. So some specifics were from some of his stuff, some MIT. It's a few spontaneous websites. But yeah, that's all I have for you guys. Hopefully